Good afternoon, everyone. Today is May 11th, 2020. Today is the last class of IME 765. First of all, let me stop the video and share my screen. Okay, so in the last class, we've already discussed the ideas of PCA and the calculation of the PCA, the principal components actually, which is actually nothing. First, we're gonna write the expression of the variance. After it, so this variance means the original variance of the original data. In detail, it is the data projected in the original R space. Okay, the the RP space. In other words, it is the identity matrix. Very easy, for an IP. So now what we're gonna do is that we want to find a direction so that the data projected onto this direction, the variance is gonna be maximized. So I set up this direction to be V, and clearly the coordinate of data xi projected onto V is gonna be inner product of xiv. And then we do exactly the same thing as what we did here. And then we're gonna get this thing. And now we wanna find out the maximum V's. Of course, V is a unit direction without the loss of generality again. So we wanna solve this problem. This problem is again a Rayleigh-Croton problem. And finally, you're gonna see any solution here is gonna be an eigenvector of this x tilde tx. X tilde means the center of the data. Okay, that means x minus where's the definition? It is it's here. Let me take out my annotate panel here. Okay, let me write a line here. It's here. Here is the definition of xt. Okay, so now what we're gonna have is just need to solve the eigenvector, so it's going to give you the optimal solution here. The problem is that how would you choose, because you do have p eigenvectors. So the thing is, because this optimal solution, sorry, this objective function, actually this equals to lambda itself. So of course you're going to choose the biggest lambda. So the vector corresponding to the biggest lambda will be our first principal component. And this x tilde v1 will be the score of this first principal component. And then how to get a second one? Similar, we're gonna remove the impact of the first principal and then get x2 tilde, and then do exactly the same thing. And here I've proved that for this x2 tilde t, x2 tilde, here all the eigenvectors will be the same as x tilde tx, except for the biggest eigenvector. The eigenvector with the biggest eigenvalue, which is already removed in the first step. So of course I'm gonna choose the second biggest one. By the way, I made a little change here. Instead of writing s, I wrote it as x tilde tx. The reason, because strictly there's going to be a very small difference, which is a coefficient here, 1 over n here. So that's a difference, although, actually not a big deal, because your lambda will be 1 over that lambda. So the biggest one will still be the biggest one, you know what I mean? Because, for example, consider s, the eigenvalue, the eigenvector of s and the eigenvector of xt tilde x. What's the difference? No difference. They are going to be exactly the same, but eigenvalues will be different, because the eigenvalue of here will be 1 over n of the eigenvalue here. It's just a coefficient here, 1 over n. See this part? So, but strictly, I still, wrote it to be x tilde t x tilde. So now we are gonna have this part, and hence it's gonna be the second, eigenvector, the second principal component will be the eigenvector of x tilde t x tilde with the second largest eigenvalue. And then we can repeat the same process, do the same, and for each time we define x tilde k to be this. In other words, the original centered data minus, the impact of all previous principal components. Previous means Suppose we know the first up to the k minus 1th principal components of x. Then to solve the kth principal component, we need to solve this problem, right? We need to solve this problem. And as what we just showed here, this problem would be what? The optimal solution of it will be the eigenvector corresponding to the kth largest eigenvalue of the original center of this x tilde t x tilde, right? And hence the whole system is going to be there. And so now everything's easy. We only need to get the eigenvalues of this part, and then their corresponding eigenvectors will be the principal values. The biggest one, is corresponding to the biggest one. That's it. And then the new system, which is composed of the full principal component and coordinates, is going to be this x tilde v. X tilde is the original center data, and v is what? Is your is the subspace created by the full principal components. Okay, so here's the story, the basic mathematics of the principal components. Any questions here? No? Okay. Again, make sure you do it step by step after the class. You must do it step by step.
I have one question.
Yes. Yes?
Yeah, here actually S is covariance matrix, right?
Yes.
Yeah, okay. So if we use like correlation matrix instead of covariance, will we get the same result?
No, because the correlation here doesn't make sense. I want the variance to be as big as possible. You know what I mean? The correlation and the covariance, although very similar meaning, but the difference is that correlation, you eliminate the variance, the absolute variance of itself. So it's not going to be the same. In general, it's not going to be the same result. And it doesn't make sense. I mean, why should you maximize the correlation here or minimize the correlation here? I don't care about the correlation. What I care is in which direction I can project to maximize, to make it, let's say, to make the data to be as different as possible. Different in terms of like the absolute value of the dispersion actually. But if you do correlation way, do that way, and then meanwhile times a variance, no, I don't think that's going to be exactly the same. Maybe up to some coefficients. Probably they will not be the same. Hello? Okay. Did I answer your question? Hello, can you hear me? Looks today the internet.
Yeah, yes.
Problem. Can you hear me clearly? Because today I'm at home. Okay. Now let's continue. So the problem here is that I still need to do the full principal component analysis. In other words, I still have p dimensions. And it doesn't really help in real applications, because as we mentioned here in this part, what you want to one very, very important thing is what? One very, very important thing is what? Is for data dimension reduction, right? If you after one, the operation, you still have the same dimensions. So why should I use it? It's meaningless. Okay, now let's see how can we really do the dimension reduction and make, in many cases, great dimension reduction by PCA. So the thing is, although here I have P principal components, the truth is that I don't have to use all of them to rebuild the new coordinate system. Why? Because think about this. So for calculating the kth principal components, ignoring, again, the S, because S has a 1 over n here. Let's ignore this 1 over n because it's a constant. It doesn't matter, this 1 over n. It's just a constant. If we ignore this 1 over n, what are we going to have? We're going to have this part, right? We're going to have this part. This part is actually what? It's actually the variance. Again, ignoring the constant coefficient of 1 over n. This is the variance. So this is actually what? this is actually the variance corresponding to the kth principal component. In other words, this is the variance contributed in the kth coordinate system, new system, right? Okay, now if that is the case, think about this. Because all of these are what? They are orthonormal vectors. Again, because V matrix is orthonormal, or you can simply call it unitary. The difference between unitary and orthonormal matrix is that unitary is, first of all, I use unitary because it's easier, it's shorter. But strictly unitary can be used even in complex matrix rather than just a real matrix. But orthonormal, usually we say real matrix. So when the matrix is real, it doesn't matter you say orthonormal or unitary, they're the same. Okay, because they're orthonormal, so you have what? The range of them equal to what? The range of P equal to RP. So in this case, what we're gonna have is that we must have this conclusion, that S is proportional to the summation of lambdas. So as long as I have this, what I'm talking about is how to decompose this variance S. Okay, so finally you must have S equal to all of this. Why? Because this is actually what? This is actually a decomposition or reset of these variances. So if that is the case, we can what? We can use the lambda to count the variance. In other words, have a look at this. Let me calculate it in this way. This K is up to the kth principal component. And this P means the total principal component. Okay, so first of all, I must have lambda 1 is greater than lambda 2, greater than or equal to lambda 2, greater than or equal to lambda 3, blah, 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 greater than or equal to lambda P, right? That is by my definition, because my first principal component is always what? Is always the most important one, or in other words, which counts for the most variance. So your lambda 1 is always the biggest. And of course, just now by definition, lambda 1 is what? The biggest eigenvalue of x tilde t x tilde. And the lambda 2 is the second biggest one, right? So this tells you what? This tells you what is the ratio of the sum of the first k lambdas versus what? All the lambdas. And you may not believe that in real applications, usually for a very small k compared with p, this part will be a big ratio. It's just like, do you know the fact that, let's say in the US, the property distribution, I mean the capitalism, the money, is very uneven. You know it? The 1% of people occupies more than 80% of the wealth of the nation, principal components. Just an example, okay, no other meaning, absolutely no other meaning, don't misunderstand. The same here, for the principal components here, L equals 1 to K. In many cases, for a relatively small K compared with P, this ratio will be a very large ratio. Could be more than 80–90%. And you're gonna see an example right here. Okay, now interesting thing is that suppose, by the way, and this is called this part. I mean, this part. This part. It is called here. It's called explained variance. This means you can use PCA, use the first K principal components to explain the variance. That's why it's called explained variance. Okay, now what we can do is that I'm gonna first determine a threshold alpha. This is like a significance level. Then what I'm gonna do is that I wanna choose the K principal, the K star as the principal components, such that at least alpha of the total variance will be considered. So what you're gonna do is right here, easy. You're gonna choose the minimum K, the minimum number of principal components, such that the explained variance versus the total variance is at least alpha. See it? Okay, so in this case, I can do what? I can reduce the dimensions. Okay, let's see the power, how useful it is. Let's see here. Let's write here. I have an example here. Let's make it smaller. Oh, you can see it. Okay, so the original picture is here, right? Remember, we have how many dimensions? 10,000 dimensions, because I have 10,000 pixels. Okay, now here is k equal to 1. Yes, k equal to 1 dimension. That means I use just the first principal component. I get this one, 1 dimension. Here I use 10 dimensions, 50 dimensions, 225 dimensions, 250 dimensions. Okay, 250 compared with 10,000 is what? It's nothing, right? It's 2.5% only. It's nothing. But have a look at the result compared with the original one. By our eyes, they're almost the same. Get a point? How powerful it is. You only use 2.5% of the dimensions and you can express the same, almost the same. Amazing. Sometimes you can use 1 as well. In some cases, personally, I prefer 1 because this 3 is even more beautiful than this 3. For example, you just zoom out, make it small. You can see this 3 is actually really good. Did you see it? If you look at it this way, and this is only k equals to 1. Amazing. Versus originally your p equal to 10,000. No. Sorry. It is here. It is here. See. Okay, let's make it smaller. See, this 3 looks very beautiful. Actually, it's better than the original 3. Don't you think so? Okay. So here's the power of the principal components. However, beginners may have a question. That was also my question when I just learned principal component analysis several years ago. I asked my professor. I said, "Hey, although you said it is, for example, 1 dimension, 10 dimension, but it doesn't make sense. Why? Because what does this 1 dimension mean? For example, let's say this is V1, right? Okay, let's have a look at what V1 is. Where's my V1? Okay, V1 is here. V1 is calculated by the Rayleigh quotient. Okay, Rayleigh quotient means what? Your x tilde, what's the dimension? N by p, right? So what is the dimension of your V1? Your V1 is p dimension, the vector. P by 1, of course. So, I mean, well, here p equals to 10,000. It seems that you still need 10,000. So where is the so-called claim, which is dimension reduction from? Because you still need 10,000, right? And you may have, for example, 250. You may need to have V250. So in this case, it looks that you need 10,000 times 250. Looks that you're gonna even need more dimensions, right? So where's the dimension reduction from? Can any of you answer this question? Get my question? Get a point? Because how would you calculate a V1, for example? V1 is a vector of 10,000 10,000 elements, right? Yeah, indeed, V1 is p dimension, right? So in this case, okay, so you still need 10,000 dimensions. And if you need a V10, that means you need 100,000 dimensions. Looks like, oh, you're rather than, dimension reduction, seems that you're increasing the dimension. So why can I claim this is indeed a dimension reduction? Now, don't have a look at it. Think about it by yourself. Any ideas?
So here, 1 dimension means 1 vector.
Yes,
like
I think your answer is
from
correct,
the
although
original
not
matrix.
Absolutely the point. But yes, I think I think you're correct. Yes, but why 1 dimension is 1 point, one vector? Or in other words, let's say let's say this in the computer storage. Okay, how would I store it? Why it is really the storage saving, for example. Remember the clustering, as we mentioned before, image storage. Remember, also a great storage saving by moving everything to the centroid, right? But here, how can we save it? Continue, Mabuba. Go ahead, use your idea. Your idea is correct, but you need to go one more step deeper. Hello, can you hear me? Yes.
Like, yes, I can hear you. Like if we had like a matrix m by n size,
Let's use
then
n by p. Let's use
suppose
n
m
by
by
p.
n. Yes, m by p. And after that, we get p number of vectors and p number of eigenvalues. So if we like when we are considering saving the data in a memory, then we save data for all the p vectors. Now, when we choose the principal component, like the largest eigenvalue related vector, then we only save data related with the largest eigenvalue related vectors. We don't save data for all other vectors. That's how we minimize the storage.
But something wrong here. That's why I said you need to be a bit deeper to accurately hit it. You're not okay. Let me explain it a bit more clear. So suppose I'm gonna save, instead of p, I'm gonna save k star. Okay, for example here, k star equal to 10, right? I want to I need to store 10 principal components. So first of all, yes, you need to store the 10 principal components. What are these? The second thing, you don't need to store the original x anymore, which is, for example, I don't know the dimension. Let's say 10 million. What is that? 10,000 times whatever, a very huge number. Instead, you only need to do what? You only need to do x tilde times this vk. This vk, sorry, I mean the v where it is, the big V, the V matrix I'm talking about. I'm talking about this. Let me write it down. Let me call it vk still, but this is big V, okay?
P by K matrix.
Yes, the matrix. Okay, I only need to store this, and what I need to do is that I'm gonna, this x should be tilde x, okay? Tilde x times vk. That's it. And consider how small it is. It's gonna be very, very small. See it? Why? Because it's gonna be how many dimensions? It's gonna be only for how many columns do I have? I only have k columns. See it? Be careful. K is much smaller, less than p. Okay. For example, k here is only 10. It's a much smaller number. In other words, I only record your coordinates on the vk. Just now, what Mahbooba mentioned was we're gonna store the vk. Actually, you're gonna store the vk plus for each data the projection onto the vk. Get a point? That means what is your new coordinate? Your coordinate on the new system, which is composed by the first k principal components. Okay, so in this case, my data storage will be much smaller. Not a bit smaller, much smaller. For example, here, suppose your n is 1 billion. For example, n is usually a huge number. Even your p here is 10 million. Sorry. Let's say your n is 1 million. Let's say your p here is 10,000. Consider how many bits you need. But if I do in this way, I can change from 10,000 to k to 10, for example. I save 1,000 times of the storage space. Get a point? That's the power of principal components. And compared with clustering, a relatively good thing is that here we can use this way, smartly define k directly. But in clustering, it is not that easy. You know, especially for this kind of image-based clustering, usually we just check our eyes. That's it. There are tons of different clustering methods. The clustering, what I mean is mostly, for example, the k-means clustering, you know, the simplest one. There are too many clustering algorithms, too many. Get a point here? That's how we can use PCA to do the dimension reduction, and we can choose the k very clearly. Okay, and in many cases, for example, in the relatively big dimension, p dimension, you only need a little k. For example, in my personal view, this 50 is great, works greatly. Even this 10 works very well versus this 110,000. You can see the power very clear. Okay, any questions here? No? Okay. Then
Yeah, I
after
have
that,
one question.
yes, yes.
Yeah, so that you are saying that we need to multiply the eigenmatrix or the some eigenvector with our x delta, right? Not with original data.
Because of this. Here you go.
Yeah, so will it be any problem if we multiply with our original data set instead of x delta? Just x delta is like subtracting the mean from this data, right?
Then your calculation will be wrong because it does not express the variance. And why just now I just smile because I did make this mistake when I coded the PCA by myself. When I was last week, 2 weeks ago, when I was preparing this lecture, so I didn't like directly use the PCA. And later, especially here, I'm gonna show you SVD. So I coded by myself, and I realized that it was wrong because I I compared my coding with the MATLAB code, I mean, directed command PCA, and it was wrong. I was thinking, how could it be? And then I realized, yes, I made the mistake. Exactly as you just mentioned, I use x times v rather than x tilde times v. Why? Because the variance is defined in this way. As the variance is xi minus xi bar. See it? Right? Let me ask you, say I give you one-dimensional data, x1, x2, x10. How would you calculate the variance? You're not going to do x1 squared plus x2 squared plus x10 squared divided by 10. You're going to do x1 minus x bar squared, right? The same, yeah. Otherwise, it's going to be unfair. Why? Because what if my x are big data? You know what I mean? For big data, let's say, for example, my x levels are, let's say, 10,000. For 10,000, for example, if I have only a change, let's say 1, it is nothing, right? But if my data is 1 or 2 or 3, that's going to be big data, a big change. That's why you need to minus this one, minus a x bar here. That's the reason. Sorry.
Means
just
we
now
always need the centered data, right?
Yeah, centered. X tilde means the centered delta, centered data. By the way, excuse me. By the way, just now what I explained, something logic has something wrong. Actually, the variance cannot easily solve this problem. What I should say is that it shows the dispersion, so that you're gonna always see how far it is the data is from the center. That's the reason why. That's how the definition of variance works. Okay. Yeah. So that's the reason why here and all our here stories. If you see the mathematics here, everything here, I use x tilde here. I cannot use x bar. And the very interesting thing is, if you check other textbooks or class notes, most of them lecture notes, they're gonna say that let x be a center data. I dislike it because in your real life you will never have an x to be a center data. And many people, I've seen so many people here confused here that they calculate x bar to be the summation of xi to p and 1 over p. That's very, very wrong. It should be 1 to n. You know what I mean? That's the reason why I would rather put this x bar here and create another notation which is called x tilde. Not x bar, okay, this is x tilde. Because if you make it bigger, you're gonna see very clear. Instead of just assume that x is centered. Many authors assume x as centered for somewhat is because for notation convenience, because you don't need to make a tilde here. You can just write the x, but it may cause confusion. Okay, so yes, you do need to center the delta, center the x first to get the x tilde, and then make it in this way. And Arab, you asked a very good question. Actually, it's a kind of like homework for you. Do it by after today's lecture. I'm going to tell you SVD, teach you SVD as well, and then do it. Let's say you just later you can see this is nothing but SVD. You can be lazy, directly use SVD to calculate it, and then use x times this v instead of x tilde times v. Compare it. Especially here, I have some very interesting graphic things that I coded by myself. I can show you today, and then do everything. And you're gonna see something really interesting, and then you're gonna see why I must time x tilde instead of x. That was a mistake I made actually. Did I answer your question? Yes. Okay. Sure. Let's save some time. Let's go to the SVD part. So here we've already introduced the singular value decomposition using the lambda of x t tilde x tilde. And now let's have a look. In the following, I will try to introduce PCA in a higher level, or let's say to make it in a view, a more comprehensive view. And we're going to start from SVD, singular value decomposition. And personally, I believe this is the most important decomposition in linear algebra, even more important than QR decomposition or factorization. Okay. By the way, here nobody call it SVF, but for QR, many people call it QR decomposition. Personally, I like it to be called QR factorization. But here, nobody call SV factorization. Everybody call it a singular value decomposition. Okay, so singular value decomposition is this. Let A be a matrix in by P, and it doesn't matter what is the rank. It doesn't matter what is the dimension. There always exists a unitary, or let's say orthonormal matrix U in Rnm and V in Rpp in a diagonal matrix, which is sigma 1 to sigma q in Rnp, where q is the minimum of np, such that A equal to V sigma Vt. So that means for any matrix, it can be decomposed by a unitary matrix times this is a pseudo diagonal matrix. I'm gonna introduce why it's not a real diagonal matrix times Vt, where V is also a unitary, or let's say orthonormal matrix. Okay. Okay. Now let's have a look. What does sigma mean? Sigma first is a diagonal matrix by this, but be very careful. Usually when we say diagonal matrix, it's a square matrix. But here sigma is n by p. Okay, this tells me what? Okay, assume without loss of generality, assume n is greater than p, because in most cases you're gonna see n is greater than p. You're gonna have a matrix sigma like this way, right? Okay, now I'm gonna have something like this. Let me change the color. The diagonal elements gonna be here. Do you know what I mean? Okay, let's see a real example. Make it more clear. Wait. Let me show you a real example. Okay, let me randomly create a matrix for fun. A equal to, let's say 1 2 3 4 5 3 5 1 1 1 2 2 2. No, let's say 1 5 10 1 2 9 9 8 1 5. Okay, let's make it to see u SV equals SVD of A. Let's have a look at S. Get a point? Why I call it a pseudo diagonal matrix? Because it's not really diagonal. It is only diagonal in the p dimension. Here, my p equals to 3 and my n equals to 5. No, and my n equal to how many? 6, right? 1, 2, 3, 4, 5, 6. Okay, yes, my n equals to 6. See it? It's dimensional only in this way. Okay, so how about this? What if I rotate it? Let's say here p is greater than n. Okay, let's play it. See what does S look like? S this time looks like this way. See it? It's only this part is diagonal. The left part is 0. See it? Previously what? Only this part is diagonal. The other part is 0. See it? Now you understand why I call it this sigma to be a pseudo diagonal matrix, and also have again read this part. You're gonna see it more clear. Sigma equal to diagonal of sigma 1 to sigma q with what? There's something here. What is this? With what? With q equal to yes.
If A is a square matrix, then sigma is a diagonal matrix, right?
Of course. If your n equals to p, then of course. Okay, so that's the point. In some books, especially including the ESL, I don't know why, but the author define the U to be N by P, sigma to be P by P, and the V to be P by, let me see. Yes, V to be P by P again. I personally dislike it. And lucky that the Bible also supports me. In the Bible or in most, let's say this kind of, professional matrix computation, this kind of books, you're gonna see the singular value decomposition is defined in this way. The way they define it is called a thin singular value decomposition, which is very rare. So I even didn't mention it in my lecture notes here. So I would strongly recommend you use this notation. It's gonna make your life much easier rather than sometimes U as like N by P and then V is gonna be P by P. It's gonna really be confusing. Why? Because here you're gonna see it very clear. U and the V are symmetric. So that later if you make the a singular value decomposition for the AT, you're gonna have what? You're gonna immediately have what here, which is V times sigma T times U, UT, right? Which is very easy. It's just symmetric. Okay, but be careful. Sigma doesn't equal to sigma T, okay? Again, because sigma is N by P, not a square. No, it's not guaranteed to be a square matrix. Okay, and here these sigmas, sigma 1 to sigma Q, they are called singular values. And all singular values are greater than or equal to 0. And later you're gonna see it very easy why all of them must be greater than or equal to 0. And also the existence of the SVD, in other words, the proof for this one can be done by induction. And I'm not gonna explain it here. It's gonna be kind of like time consuming. And a very important thing of SVD is that it exists for any matrix. It doesn't matter whatever matrix it is. No matter what is the dimension, whether it's a square or not, whether it's a full rank or not, as long as you have a matrix, I have the singular value decomposition. Even if it is a complex matrix, you can still do the same. You still have a singular value decomposition. But here in this course, again, we don't consider the complex things. I assume everything is real. Okay. Okay. Now, geometrically, let's see what does it really mean. Because I don't want you to brutally memorize this. This formula is really boring. I want you to see the vivid picture, and I'm gonna show you this very clear example step by step. Okay, now let's consider for whatever matrix A in N by P and for corresponding vector X, I have this. Mahbuba, you should never forget that because you made mistakes on this for too many times. Okay, never forget about this. Extremely important. For Arab, I don't know whether you've seen this before, but this is very common, especially in matrix computations. Okay, now let's see. What does singular value decomposition mean? So first of all, you need to know what is AX. Here, let's do experiments right here. Let me make a 2x2 matrix because I need to plot it in 2D. Let's say, for example, let's say 5, 2, 1. Or do you have any suggestions? Otherwise, you may say that I'm cheating. Can you randomly give me a 2x2 matrix? Any, but don't make it too big because I want it to be relatively small so that I can show something more clear. I mean the numbers. Any idea? Are you satisfied with this number? Okay. Now let's do this. What is that? Okay. Yes. So now I've defined an A here. Let me delete all this. Yes, I'm gonna show you what does AX mean. If AFX is a circle or a disk. Okay, here which code is let me see. I think it's the matrix illustration something. Okay, here matrix rotation illustration. So here's my code. I can directly show you my code. What I'm gonna do is that I'm gonna create AX, which is a circle, unit circle. And then I'm gonna do A times X, and I'm gonna plot it. And I'm gonna see what does it look like. Here we go, it's here. That is what does it look like. So this point is the origin, 0, 0. And this blue solid circle is the X, that X equal to 1. X norm equal to 1, what I mean. This is a unit circle. And this is the contour of AX. In other words, guys, what does AX do? AX first rotate your X circle, which is the unique circle, and then stretch it, right? stretch it towards this direction and this direction. See it? You know what I mean? So in other words, what it does is, let me use a smaller one. Okay. So consider originally I have these two vectors, canonical vectors or whatever you call. And then what is it? It does at first, I rotate your canonical variance, your canonical vector to, let me use, let's say, green color to here. I make a rotation here, right? And then kind of like I stretch it. I stretch this part to this part. That's what AX do. Okay, now I'm going to show you that actually you can what? You can use singular value decomposition to do the same. However, you do need 2 rotations, which is very important. Let's see how it could be possible. And I coded another thing. I forgot which one. Let me see. PCA illustration, I remember it's called. No. SVD. Okay, this one. So here's the thing. So basically what I did is the same. First, I input in A, and then I calculate the singular value decomposition. Here I'm cheating because I directly use MATLAB. Later in the lecture, I'm going to show you how to do it, which is actually very simple. And then again, I make a unit circle of X. And then I just calculate, A times X, and then step by step do the singular value decomposition. And then I plot all of this. Let's see. How does it look like? Okay, here's the result. I don't know why the result always show this way. Let me close it and reshow it. Otherwise, you may say that I'm cheating. That again shows from here. Okay, I'm not, just to let you know, I'm not cheating because I have double screen. Okay, so this is the original disk. X norm equal to 1, the original unit. Okay, remember what the singular value decomposition look like? Singular value decomposition looks like this, right? You have A equal to V times, I cannot, write sigma, so I write S, okay, times V prime. V prime is VT, right? This is singular value decomposition. Okay, so if I have AX, then what do I have? I should have this, right? AX equal to this, right? So what I'm going to do is that I'm going to decompose that step by step. Here, 1, and then number 2, and then times U. So they should be the same. Okay, let's see. So this part is original disk. So this part is here, V prime times X. You see? All here are green, sorry, are blue circle, and here's kind of like a partially like blue and a partially red. You know why? Because what it does is a rotation. So it's gonna, for example, if you have 2 canonical vectors, what it does is that it's gonna circle it, make it, for example, something like this way, for example. And that's why, of course, it's still a circle. So these two coincide together, so you cannot see it. But what it does is a rotation. Okay, now I'm gonna do this step, which is V times, S times V times V prime, which is here. This is sigma times V prime, VT times X. So see it? This is still this, this blue one. This is still the same. This blue circle here as this blue circle, exactly the same, all the same. But the difference is that I stretch it because I times a sigma. In this direction, I stretch it to sigma. In this direction, I stretch sigma 1 times. And in this direction, I stretch sigma 2 times. Can I write here? So this is sigma 1. This is sigma 2. Okay. This sigma 2 is too ugly. Let me rewrite it. Sigma 2. And because by definition, my sigma 1 must be greater than or equal to sigma 2. This is 2, not 1. This is 2. Okay, so I stretch it. And then finally, I multiply a U again. So this is, here we go. So this is the final. I multiply U times sigma times VT times X. And then see it? What I do here is, again, I make a rotation. I make it to be, sorry, this one to, why cannot, I cannot erase. Okay, this one something wrong. That I should make it here. I should make it to here rather to here actually. Okay, so now I make a rotation such that my sigma 1, sigma 2, the two principal components. No, sorry. Here's no principal component. The two singular values becomes in this way. See? So again, original, rotation, stretch, rotation. See it? Very clear. Okay. Let me see. From here, whatever. Make a bigger one. Bold. Yellow color. So here, this is rotation, stretch, again rotation. So this is the result of U sigma VTX. And this is the direct result of AX that I just showed you before. And see, they're exactly the same. Got it? Okay. And now let's go back to the lecture. And here we go. I don't know what is this X actually. I just randomly draw it, whatever. So here, let's go back. The original unit circle is in this way. And then at times a VT, as we just showed, we just saw as a rotation. And then times a sigma, it's a stretch. So for this, because it's a circle, so for a circle, whatever the dimension, the radius or the axis is always 1, right? Because it's a unit, it's always 1. Now this tells me that, okay, towards this direction, I stretch x sigma 1 times, which is the first singular value. Towards this direction, I stretch sigma 2 times, which is the second singular value. Okay, now I times the u again, which makes a rotation. By the way, why multiply by u and vt are rotation? Because they are unitary matrix. For example, sine, cosine. Remember the matrix of the rotation matrix in what? In 2D. Remember it? As long as you time a unitary matrix, it's gonna be a pure rotation. Okay, so here we go, and this is exactly the same as AX. In other words, the singular value decomposition is composed of 3 steps: rotation, stretch, rotation. Clear? And after it, I'm gonna show, the descriptions are here, but as long as you understand this part, it's gonna be very easy. Please read it after the class by yourself. And here, I'm gonna show you some properties without proof, mainly because the proofs are really, really simple, except for the last one. The last one is a little bit, needs a little bit trick. So the first proposition is that the sequence of singular values are unique. And if singular values are all distinct, then the sequence of singular vector is also unique. This is mainly in the calculation, you're gonna see why. And okay. And the second property is that for I equal to min of from 1 to min of NP, I must have AVI equal to sigma UI and ATUI equal to sigma VI. That's also very simple. Why? Because of this. Because let me write. Because here you have A. Here you have A. Let me change the color, make it more clear. Let's say this. Here you have A equals to U sigma VT, right? So you multiply the U and the VT left and right side. You have what? You have UT A equals to sigma VT. And here you go, these two conclusions. Isn't it easy? Or you can do the same. For example, you can multiply V here so that this is AV equal to AV equal to U sigma. Okay, because they are orthonormal, so that VTV equal to VVT equal to UTU equal to UUT equal to I. Sorry, I cannot say equal to V and U are not, they are not the same dimensions. So UUT equals to UTU equal to IN, and VVT equal to VTV equals to IP. Okay, so that you have this. And the third one is even easier. The third one is the rank of A equal to the rank of sigma, equal to the number of positive singular values. Why? Because A equal to U sigma VT, right? U and V are what? Are unitary. Of course, VT is also unitary. Unitary means what? Full matrix, full rank matrix, right? Do you know that the rank of A times B equal to, when the B is a full matrix, then it's equal to the rank of A. I'm talking about the rank of AB equal to the rank of A if B is a full matrix, full rank matrix. So the same, U sigma V, U and V are full matrix, full rank matrix. So rank A equal to rank sigma. So because rank sigma is a diagonal matrix, so what is the rank? And we know that all singular values are non-positive, are non-negative. So it's simply equal to the number of positive singular values. Done. And the fourth one is if rank A is R, then we can decompose it in this way. Okay, the 21A you can write it just by definition as what I just wrote there. Very simple. The null and the range here can be verified by the definition of the null and the range. Done. This one's a little bit more difficult. Have you, especially Arab, have you heard of the matrix norm instead of the vector norm? Matrix norm I'm talking about. For the matrix norm, it's formally defined in this way. Again, don't be confused by the mathematical formulation. Try to understand it. The understanding of this one is very simple. That okay, the understanding of this one is very simple. That okay, given an A, I do the AX where X is a unitary. X is a unit vector. So this tells you that, okay, AX is what? AX is a point from, you know, kind of like, for example, here, look at this. This is AX, right? Do I still have the picture? Yeah, I still have the picture. So this is AX. For example, I give you a point, for example, can I make it bigger? For example, I give you a point here. Oops. I give you an X here. For example, suppose this is X. AX may equal to this point, for example, right? I give you X, you get an AX. I give you X, you get an AX. Okay, look at here. Here, by definition, what does it say? It says that find the X such that AX, so AX is what? Is a vector, right? This norm is maximized. What does it mean? This means that, okay, so in which direction, which X in this circle is gonna give me such that I can get this one. Because this one is what? The largest norm. See it? Okay. In other words, the norm of AX as or the norm of A is what? What is this? This is sigma 1. Get a point? So if you understand it very well, geometrically directly show it. You don't have to use use this kind of algebraic proofs. However, you do have the algebraic proofs. Why? Because A equal to U sigma V. And the UV are unitary matrix, so game over. So it's equal to the norm of sigma. And by this definition, sigma is what? Sigma is sigma 1, sigma 2, sigma 3, right? And then this is 2 norm. This is L norm. So in this case, you make it L norm there. L is greater than or equal to 2, okay? Let's say it. Or greater than or equal to 1. And immediately you're going to get what? You're going to immediately, well, I think I have a mistake here. Okay, here's A2, sorry. So this L equal to 2. In the 2 norm, you're going to directly get what? This must be sigma 1. The second part is a little bit more difficult. You need to have a bit more skill to make it. So this Frobenius norm means the summation of all elements square, sum of all element squares of this. And it can be shown that the Frobenius norm equals to what? Equals to the sum of all singular values. And this needs a bit more decomposition here about the Frobenius norm. And I'm not going to expand it here a bit more. You're welcome to explore it after the class, okay? So these are some very simple and important concepts of the singular value decomposition. Any questions here? Especially the understanding of the geometric. Regarding these parts, you can read it by yourself or try to write it by yourself. Again, as a proof, as an exercise after the class, try to write the proof very clear, step by step by yourself. Again, do it by yourself rather than verify it. You know, reading a book, a very bad point for many people are just to verify it. No, do it by yourself. And then just to check the answers. That's how to read the book. Okay, so after it, I'm going to introduce the calculation of SVD, because here we mentioned how good SVD is, but in the real case, I give you a matrix. You need to calculate an SVD for me, right? How to do it? Okay, so because A equal to U sigma VT, so we must have AT equal to V sigma t ut, and that's also the reason why I want to define SVD in this case. Otherwise, you know, U and V, if they are not square matrix, Jesus, you're gonna make yourself very, very troublesome. Okay, now good point is that U and V are what? They're square matrix, so matrices, so it's gonna be much easier. And hence I have what? I can calculate VTA and AVT, sorry, ATA and A, and also VAT. So finally, you're gonna have this, wait a second. ATA equals to this. Be careful, this is P by P. And AAT is this. This is M by M. Okay, so now let's see, what are these? Because I have here sigma T sigma and sigma sigma T. Without the loss of generality, here we assume N is greater than or equal to P. Okay, now let's see what are the form of sigma T sigma and the sigma sigma T. We'll have this. No matter what, the main part of them would still be this. No difference. But the difference is at the dimensions, because sigma T sigma is P by P. Why? Because your sigma is N by P. And your sigma sigma T is N by N. See it? So this gives you sigma sigma T and the sigma T. This gives you sigma T sigma and the sigma sigma T in this form. But no matter what, both of them are diagonal, right? Okay, both of them are diagonal. And you know V, U are unitary, or let's say orthonormal matrices. This tells me what, guys? This tells you what? Eigenvalue decomposition. Why? Why this must be the eigenvalue decomposition? What is the definition of eigenvalue decomposition?
It's eigenvalue decomposition for A transpose A matrix.
Yeah, of course. Yeah, because ATA equal to this form, not A equal to this form. Yes. And that's also the relationship between the eigenvalue decomposition, between the PCA and the SVD. But here, yes, indeed. Why? Because what is the eigenvalue? Eigenvalue is this, right? Eigenvalue or eigenvector is something, for example, you will have, for example, let's call ATA to be B, okay, make my life easier. You will have BV equal to lambda, what does lambda call? Let's say lambda called LV, right? This is the eigenvalue to other. Let's say, can we make a bit more beautiful? Let's say W. Let's call W to be eigenvalue, okay? So this is eigenvalue, V is eigenvector, right? So if you write all of them in matrix form, what does it look like? It's going to be BV equal to diagonal of W1, okay, W1, blah, blah, let's say W, how many? WP, for example, and V, isn't it? And see here, what do you have? You have ATA times V equal to this, right? And then what do we do? What we're gonna do is that we're gonna do what? We're gonna, for example, times VT here. Or let's say do this. Wait a minute, guys. I realized I made a mistake here. I should have write it in this way. Sorry. So I times a V, both V in right hand side. So in meter I have ATA times V equal to what? V times this diagonal matrix. See it? Exactly what? Eigenvalue decomposition. And exactly the same for what? For AAT. Okay, now you get it. Why? Because the eigenvalue decomposition of will give you lambda, but we know that lambda 1 should be equal to sigma 1 square, and lambda p should be equal to sigma p square. And here, lambda 1 to lambda p the same, but lambda p plus 1 is 0 till lambda n. Again, I assume n is greater than or equal to p, okay? See it? And hence what we have, okay, now I write a notation this way. So I let lambda I, at a subscript of ATA, this one to indicate the lambdas of this matrix. And I assume, of course, lambda 1 is bigger than lambda 2 is bigger than lambda 3, the i's largest eigenvalue. In meter, I have what? In meter, I have sigma I square equal to this. And similar thing is this, where it is. I also, for the AAT, I also have this, right? And of course, these two would be the same. Why? By the lambda polynomial theory. For the polynomial of A, the lambda of that new matrix would be the polynomial of the previous lambda. Done. Okay. So here it's kind of like a square because in the sense of a square, although not the real square, because you have ATA. Okay. So what I know is that first I can use this method to determine the lambda, to determine the sigmas, right? Sigma equal to the square root of sigma I equal to the square root of this lambda I ATA first. And the second thing is what? What are the V and the U's? These are what? Exactly the eigenvectors, the collection of eigenvectors of ATA. See it? Corresponding to the largest VI is corresponding to the sigma, this sigma 1. The smallest VI is corresponding to this smallest lambda I. And the U's are what? Are the same, the corresponding eigenvectors of AAT. And hence, as long as I do the eigenvalue decompositions of the AAT or ATA, I'm going to get the U and the V and the sigma. And I'm done with singular value decomposition. Got a point? Okay, let's see an example. Again, let's use MATLAB, mainly because I'm lazy. I don't want to code by, kind of like really code by myself. Let's verify the conclusion, whether it's correct. Okay, let's make a matrix B. Let's make it a bit more difficult. I don't want to make it to be, let's say, kind of like a square matrix. Let's randomly find some number. Who knows what is that? How about we make it to be, let's say, 3 by 5, let's say. 1, 2, 3, 4, and then for example 4, 4, 3, 3, 10, 5. Okay, so this is, first of all, let's calculate what is SVD. SV equal to SVD of B. Okay, here I have the SVD already. Okay, let me do this. Let me directly show it. Let me directly show it. Okay, so in this case, you can see UVD. Okay, now let's do the what? Let's do the eigenvalue decomposition. Let's say V1 D1 equals to eigenvalue decomposition of, what do we have? We're gonna have V prime times BTB, right? Okay. Compare this V1 with this eigenvalue decomposition V. Sorry, this is that V1 is from eigenvalue decomposition, right? And this V is from singular value decomposition of B. This is the eigenvalue decomposition of B prime times B. Look at this. They're the same, see it? But you have to exchange the rows, the columns, sorry. Why? Because the biggest eigenvector is here. So the corresponding V3 should be the first singular value decomposition, the first V in the singular value decomposition, and it's here. See? You can ignore the negative, it doesn't matter. It doesn't matter, because it's also normal. And the second biggest one is here. So this must be the second column. See it? Second column here. And the third one is here. And here we go. This must be the third column. So here. What I'm saying is actually this. Let me show this. This is the first part, this is the second part, and this is the third part. See it? The same. Okay. Now let's play what? Let's play for BT. B times BT. Again, see it? Regarding these two columns, because they are 0, so it doesn't matter about the orders. But I do care about what? I do care this versus where? Versus the U here. And okay, let me show U and the D2 more clear. U, D2. See it? Wait, V2, not D2. See it? So the biggest one is here. So, and hence you have what? This and this. See it? The second biggest one is here. This is this. The third biggest one is here. This is this. And the other two, it doesn't matter about the orders, or even doesn't matter what else it is, because they're 0. They're 0. The eigenvectors are 0. The eigenvalues are 0, right? So we can play whatever you like, as long as they're orthogonal to the previous one, it's done. Because it's 0. 0 times whatever is 0. So it doesn't matter. So these two, it doesn't matter what they are. You might say, hey, these two are different. Who cares? As long as they're orthogonal to each other, it's done. Orthonormal to each other, it's done. Get the point? That's how we calculate the eigenvalue decomposition. So sorry, that's how we use the eigenvalue decomposition to calculate the singular value decomposition. Any questions here? No? Okay, now let's have a look at the relationship between SVD and the PCA. So from section 2.1, which is here, we've spent a long time introducing how to calculate the PCA, right? We've seen what? The kth principal component is what? Of the data X as the eigenvector of this x tilde t x tilde corresponding to the kth largest eigenvalue, right? And then from this calculation part that we just introduced, we know what? The VI is also the eigenvector of the ith largest eigenvalue of this. And that means what? That means they're the same. See it? The kth eigen principal component versus the kth, let's say, largest eigen of the kth, let's say, eigenvector corresponding to the largest eigenvalue of this. And hence, actually what? Hence, actually PCA of X is equivalent to the SVD of the centered data X tilde. And the VI is the ith principal component of X. This VI means what? This VI means the ith, this VI means this, the singular value decomposition V. Where it is, this V. The reason I didn't claim because in both systems I use the same V. That's the purpose I use the same V. In the text, not textbook, in which book? That book, they used the U, and I feel it's going to be confusing because you may think it's from here. No, it's from here. That's why I use them, both of them, to be V on purpose. And here you can see it. For example, I denote the k principal component to be VK. See it? And here I use the same V because they're indeed exactly the same. Okay. So here you go. Of course, the singular value is the square. Don't forget to square it. Okay. For example, here. Let me see. Where is my MATLAB here? So you can see what they are. Let's say D1. D1 this, right? But what is S? S is this. See, they're not the same, right? Of course, because you need to square it. You know what I mean? Because sigma square equal to this. So you need to do the SQRT of D1. I don't know when it's going to be error. Oh, what happened? Oh, okay, yeah, order, yeah. Oh, scare me. This is this, order is different. So here is here, this is this, okay? And they're the same, see it? Don't forget square root, okay? Otherwise, they're not the same. Because why? Because the proof here I've already showed it. It's the square root. Sigma square equal to the lambda, okay? Any questions here? Okay, in the end, let's play one more game, which is again the same. So I have the B, right? Okay, let's play PCA. Let's say what? Let's do this. So let's see. Oh wait. My USV is what? It's already the SVD of B, right? I forgot of B. Okay, yes. Now they're the singular values of B. Okay. Now see what? We're gonna do the PCA of B to see. We're gonna do the PCA of B to see whether they are the same. Do you think they're the same? Arab? Arab, do you think they're the same? Hello? Arab, can you hear me? Arab, can you hear me?
Yeah.
Yeah. Do you think
Yes.
they're the same? I do
Not
the
sure.
single. Huh?
Not sure.
No,
I
not
don't
sure.
know.
You know why I ask you? Because I use B instead of tilde B, so that they should not be the same. I played on purpose. Be careful about this. The PCA of X is equivalent to the singular value, a singular value decomposition of tilde X. Okay, so when you center it, they're going to be the same. And if you directly do it, that's not going to be the same. Let's see it. Okay, so here you go. And the PCA is in this result. See it? Look at this V versus this. They are not the same. Okay, now let's do how to center it. Center it is B minus bar. No. What's the one? Mean. Thank you. In MATLAB, it is mean. And they should be the same. See it? They're exactly the same now. Huh?
No.
Sorry. No, my fault. It should be this. It should be here. Here. SVD. Okay, sorry. Let's do this again. CLC. So PC's principal components equal to PCA of B. So this is one result, right? And now let's do this. USV equal to SVD of B minus mean B. Okay, now compare the V with this one. Are they the same?
Yeah.
Here you go. Easy. Don't forget it, okay? I played that on purpose. You need to B minus mean B rather than directly the B, okay? If it's a B. So you know, did it answer your previous question? Why wouldn't you shift it to the center of data? That's the reason, because otherwise the definition is wrong. The definition is I want to make the dispersion to be as much as possible. If I do not minus the mean, it's not a real dispersion. It doesn't work. That's the reason. Okay. Okay, very good. That's everything about this lecture, and actually that's also everything about the machine learning class taught for the whole semester. Thank you very much, especially for Arab. You are the VIP, as I told you. Okay, so in this summer, if possible, I'm gonna add more things to this machine learning class. Try to make it a bit, have more things inside, because as I designed the machine learning class, again, without deep learning, should be 2 semesters. And it's extremely important. Unlucky that we don't have a very comprehensive class for OR, because in my personal understanding, we should also have 2 classes about the advanced OR, I mean the PhD level, so that it's going to be partially kind of like linear programming plus nonlinear programming. When I say linear programming, what I mean is conic linear. Doesn't mean the traditional linear, because nowadays you need to know something about CLP and also SDP is this kind of things. SDP means what semi-definite programming. Okay, so it's going to be more clear after learning that, and after learning the statistics, more higher level about the statistics, and then you learn machine learning, 2 classes of the machine learning. The whole system going to be very good. But unfortunately, actually, the department is trying very hardly to do it, but because we don't have enough professors, so we may not be able to make it, make it possible, make it, come true. However, I will try my best to add these kind of things. Later, I will have a website and put all these kind of things to the website. So because learn by yourself by reading this kind of notes uploaded to the website. And again, all the things that I wrote here, no copyright. Feel free to directly use it. I don't care, as long as you keep my name. Don't remove the name to your name. There's no copyright. Feel free to let your friends or whatever, whoever use. Again, I believe that knowledge should be free for all people, and that's also the reason I want to create it. The purpose is to let people to use rather than earn money. Okay, that's everything. Thank you very much. If you have any further questions, please let me know, and feel free to contact me by email or something. I think the whole summer I will be here. Yes. Oh yeah. Regarding the final exam. Yeah, the final exam I will give you on Wednesday, afternoon. So the due date will be Sunday. You should have enough time to solve. No worry.
It will cover regression and
everything. But the main part, of course, will be the second part. Why? Because what? Because for the unsupervised learning part, I didn't give you homework. Remember it? I actually had another homework, but another homework due to some reason, the time mostly, I put several problems to be the midterm exam. That's why I didn't give you the homework problem for the classification part. But I'm gonna remove 2 of them to this final exam. So the same. It's corresponding that you finish the homework, and also more part will be about also the linear regression and also the unsupervised learning things, which is clustering plus the PCA part. Yeah, no worry, because you have 4 days and it's open book, open, internet. I think it should be okay. It should be fine. Don't worry about it.
Yeah.
Okay, that's everything. Thank you. Of course, you need to try very hard. Thank you very much for the whole semester. And bye-bye.
Thank you.
Thank you. Bye.
Yeah, thank you. Bye.